Hello and welcome back. So in the last couple of videos, we've been working through nodal analysis, kind of our first example in nodal analysis. And in the last video, we sort of wrote our one equation that we need for this for this circuit. We've written kind of the important equation for the circuit, which is the current that goes into a node equals the current that flows out of a node. So a couple of things just to refresh from this last video is that we write the number of equations and also the number of unknowns, the number of unknown voltages that we will have in a circuit, is going to be one fewer than the number of nodes. And really what we're going to do here is we are going to write an equation for every single node that is not the ground node, every single node that we do not ground. So, and you can also imagine, so in the last video that we wrote this equation, we said that what goes into our node V0 is 2 amps, so we have 2 amps going in, and then also our current I1 goes in. And that was equal to what flows out, which was 7 amps, so 7 amps flows out. I2 flows out right here, and our current I0 flows out. I0 flows out right here. We could, if we wanted to write another equation for our ground node, notice that everything that flows into the ground node, into our ground node here, is exactly equal to what flows out of our V0 node, right? So really, if we wanted to write our current in equals current out equation for this ground node, all we would do is we would multiply this equation that we got here by a -1. So really, if we wrote another equation, we wouldn't really get any more information from it, right? We've kind of like that equation gives us nothing new about the circuit. We've described this circuit as best we can in terms of current in equals current out, or we've described it really fully in terms of current in equals current out. And we've only needed to do that for one node. And generally, we will need to do that when we do these circuits for one less than the number of nodes that we have, or every single node except for the ground node. So anyway, that's kind of the important stuff from the last video. So now what we are going to do is right now we've got one equation and we've got 1, 2, 3 things in this equation that we don't know. We've got one equation and 3 unknowns. So we are not really going to be able to solve this. We don't want one equation and 3 unknowns. We are going to have to figure out a way that we can sort of tie all of these things together, that we are going to be able to relate all of our currents I1, I2, and I0 together. To do that, let me just go over to the side real quick. And what I want to do, I want you to draw on your paper just a resistor, just a general resistor, not connected to anything, or just kind of abstractly connected maybe to something. And imagine that I put a current that I am going to call VA, or I'm going to put a voltage called VA over here. This resistor has some resistance value R. And I'm going to have another voltage over here, VB. And I want to know what the current through this resistor is. So now we all remember Ohm's Law. We remember that the voltage across a resistive element, so the voltage across a resistor, is going to be equal to the current that flows through that element times the resistance of that element. So that is our Ohm's Law, V equals IR. So now, if I just rearrange this, what I have solved for over here, back in my equation, so back in my equation over here, I've solved for current. All of these numbers that I have, what these numbers represent are currents. Like that's what this equation essentially represents right now. So let me just go ahead and rewrite Ohm's Law over here, and I'm going to solve for I. So V divided by R is going to be equal to I. So the voltage difference that I have across a resistor divided by the resistance of that resistor is going to be equal to the current through that resistor. So now, if I label that I right here, how could I relate this current through that resistor to this voltage A, this voltage B, and this resistance R? Like really what makes the most difference across a resistor is the voltage difference. I don't care if this is, you know, 1,000,000 volts and 1,000,005 volts. It's the same exact thing as if this were 0 volts and this were 5 volts. You know, in the abstract, it's the same thing. If this were actually 1,000,000 volts, it would be somewhat different. You'd have to worry about breakdowns and all of that. But if we're saying in the abstract, in general terms, what we care about is the voltage difference across this resistor. And always what we think of, the way that we think about the current flowing is that a current across a resistor is going to flow from the positive voltage, from the higher voltage, to the negative voltage. And you can always think about that like, it's sort of like air pressure, right? If like wind is going to flow from areas of high pressure to areas of low pressure. And what we care about in wind is like what the pressure difference is between 2 points. That's going to give us some type of information about how fast the wind might blow. So in this situation here, what I really care about is what is the difference between my voltage A and my voltage B. So I can rewrite this current I is equal to the voltage difference, and I can write that as my high voltage, VA, minus my low voltage, VB. And then I already know my resistor value, divide by R. So I can rewrite this sort of in terms of two different unknown voltages. All that I really care about is what the voltage difference is between them. So now if I go back to my circuit and I use, let me see, I can kind of, okay, I might have scrunched this too much. Let me actually shrink this down. Okay, there we go. So we can fit that all on the screen. So now if I use this equation that I just got, and I want to rewrite all of these currents that I got, all of the unknown currents, like I already know 2 amps and 7 amps, but I want to be able to rewrite these unknown currents that I have, I1, I2, and I0, in terms of the voltage difference across the resistor divided by the resistance of those resistors. So let's just go ahead and do that. So let's go ahead and rewrite this equation. So now I'm going to sub in this equation that I got. So the 2 is going to stay the same. So I still have 2 amps over here. Now let me rewrite I1. And let me actually, here I'm going to change colors for this so I can color code everything. So I1 is going to be equal to the voltage difference across this resistor. So now remember what we said up here. Current flows from the positive voltage, the higher voltage, to the negative voltage. So look at how the current I1 is flowing. It's flowing from the bottom up to the top. Now we know that the bottom is at 0 volts. We've defined it to be at 0 volts. But for our abstraction, if we want to find this current I1 that flows from the bottom of our circuit to the top of the circuit, we are obligated to call this the positive side, this the positive side of the voltage, the higher voltage. The higher voltage is on the bottom, and this is the negative voltage, or the lower voltage. Because a current, if we define our current I1, the current is going to flow from the higher voltage to the negative voltage. Now, when we solve for it, it could very well turn out that I1, this I1 that we've defined, could be negative. That would actually mean that current is flowing from the top of the circuit to the bottom of the circuit. However, that could very well be, but if we assume a current direction, we really want to stick to it. And if we stick to this current direction, we have to say that the bottom is the high side of the voltage, the top is the low side of the voltage. So on the bottom, on the high side, we have got 0 volts, right? Because the bottom is our ground node. So my VA in this equation for I1 is going to be 0. So that's my VA, my voltage on the starting side of where the current is. And now I'm going to subtract the voltage that's on kind of the finishing side of the current, the lower voltage for this current. And that's going to be V0, my unknown voltage, one of the things I'm trying to solve for. So I've got 0 minus V0, and then the last step is I have to divide by my resistance value. And my resistance value for this resistor, for my resistor that I1 is flowing through, is 5 ohms. So I'm just going to divide by 5. So that is my current I1 that's been rewritten in terms of a voltage difference divided by a resistance. So that's our first current. Let's go ahead and move on to the right-hand side of the equation. So we've got equals, that 7 just comes right on down, so 7, we don't have to do anything to that, plus the next current we've got is this I2. So I2 is this current right here. It starts it flows from our V0 node down to our ground node, down to our 0 volts node. So going back to our abstract resistor over here, our general resistor, the current has to flow from the higher voltage, from the high side voltage, to the lower voltage. So the higher side of this current that we've defined, this I2 current, is going to be V0, right? Because everywhere on this node, the voltage is going to be V0. So the high side of the voltage, let me go ahead and say that this is our I2. The high side of the voltage is going to be V0. V0. And that current is going to flow from the high side to the low side. So the low side of this voltage, I2, is going to be 0 volts. So I say minus the low side of the voltage, so minus 0 volts. And then the last thing I have to do is I have to divide by my resistance value. So I divide by, in this case, 9 ohms. So V0 minus 0 divided by 9. So I have represented my unknown current, I2, in terms of a voltage difference divided by a resistance. So now we've only got one more of these to do. So I'm going to add on plus my current I0. And I0 is another thing that I kind of asked for at the beginning of the problem. So we are going to have to discretely solve for this value I0. So I start off with I0, and I0 also, just like I2, it flows from top to bottom, right? So the high side of my voltage, the positive side is going to be here. That positive side is going to be V0. So going back here, the positive side of the voltage is V0, and it's going to flow to the lower side of the voltage, to the lower voltage. And in our case, that lower voltage is the ground node, is our 0 volts ground node. So minus 0. And now, just like in the other situations, we are going to divide by the resistance. And our resistance for this particular resistor, the resistor that I0 flows through, is 7 ohms. 7 ohms. So our I0 current can be rewritten as V0 minus 0 volts divided by 7. So now we're pretty much done. And notice what we have done when we have rewritten this in terms of voltages. We have now got one equation, and one unknown. One unknown, right? I've just got one equation, I've got a bunch of constants here, and the only thing that I don't know what it is in this equation is V0. So if I simplify this equation, if I just use algebra to simplify this equation, I will figure out what my voltage value V0 is. I am once again pushing 15 minutes for this video, so I'm actually going to stop here, and in the next video I am going to solve for this V0, and that's actually something that you should probably do on your own. Maybe before you start watching the next video, try to get V0 on your own, and also try to get I0 on your own. So anyway, I guess that's it for right now. Thanks for watching, and I'll see you in the next video. Bye.